Hey everyone. So in this video, what we're going to take a look at is, I don't know what the right word there would be, uh, inclined planes. How do inclines change how we approach a force problem or dynamics problem? Um, what will that mean in terms of moving forward? Um, so let's go. Let's get after it. All right. So I'm going to share my screen. Bum 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 bum. All right. So, honestly, there's really just like one or two kind of major changes that go from like a horizontal surface to an inclined surface, but they're important and they show up and they actually become pretty significant. Okay, so let's take a look. Okay, let's say we have an inclined plane that looks like this. Okay, and we're just going to have a very simple system where we have a block. Okay, is on the surface. Okay, so the question could ask a variety of different things. It could ask for the acceleration. It could ask for the mass. It could ask for maybe if there was somebody pulling up here or pushing up this way. Is there friction? So they could ask about a coefficient of friction. All sorts of stuff. All sorts of stuff. Okay, so you really just got to look at the question and say, all right, what are they looking for? How can I approach it? What's the system look like? All that kind of stuff. And to do that, well, we're going to follow the same steps that we'll always follow. Okay, what's step one? Step one is draw a free body diagram. Okay, so this is one of the first sets of changes that we're going to see when looking at a object on an incline versus a nice horizontal surface. All right, so let's take a look. I'm going to draw my dot for my free body diagram. Okay, that represents my object. Okay, and we got to think what forces act on the box, the object, whatever it is. Well, we know that Earth is acting on it through gravity, and gravity always acts straight down. Okay, so we'll label it, of course, force of gravity. Okay, now let's say we're looking at another force. Well, it's on a surface, so that means there must be a normal force. Okay, but one of the key differences here is normal force is no longer straight up. Remember, the definition of normal force is a force that is perpendicular to the surface. Okay, so if this is the surface here, okay, perpendicular to that will be kind of up this way, right? So we'll see. I'm going to get rid of that. I just don't want that there. And our normal force will be up this way. Okay. Now, it's important to note that because of the fact that normal force is not directly above gravity, it's not going to equal gravity. Sometimes, when it's on a horizontal surface, the normal force will equal the gravity. Not all the time, but a lot of times. In this situation, it definitely won't be. Okay? All right. And now, without any other forces acting on this object, like nobody pushing on it or pulling it or anything like that, right? We can assume that it's going to try to slide down, right? Gravity's going to try to force it to slide down, which would mean friction would slide this way, okay? Which would be parallel to the surface, right? Kind of along the surface. Okay, good, good. Now, here's one quick thing to realize before we move on to like the next step. Normal force is perpendicular to the surface. The force of friction is along the surface. So if the force of friction is along the surface and the normal force is perpendicular to the surface, that means that those two angles, those two vectors, I mean, are perpendicular to each other, right? So that's a 90-degree angle right there. Okay, so great. So now, what's step two? Okay, well, step two would be make our net force equations, right? To make it easier, we always break them up into our dimensions. So we'll say net force in the x equals and net force in the y. Okay, so now let's take a look. I'm actually going to change colors a little bit just so we can have a little bit of contrast. I like purple. Y'all know I like purple. Okay. Now, typically, we look at our y dimension looking like this, right? where this is y, and this would be positive y up here, and our x like this, okay, where this is our positive x. Okay. Now, we can still do it this way. There's nothing wrong with that. But it's going to be a bit more complicated if we do that. Okay? Because here's why, right? I'm going to change colors again. Let's go with green. Now, if we keep our axes just like this, that means as the block slides down the ramp, okay, it might accelerate down this way. So that's our acceleration vector and our velocity vector. Well, if we do that, then we're going to have to keep in mind some components. There's going to be a horizontal component of our an x component of this acceleration and a vertical or y component of this acceleration, which makes it complicated. And then we even have to change the angles, right? So let's say we're trying to make our net force equation, right? We'd have, okay, well, the x, right? That if that's theta, actually, sorry, no. Sorry, let's do this. Don't want the green. That's what I was trying to get rid of. Right? Then this might be theta. Okay, which then makes this 90 minus theta, and then this is theta, but then this is also 90 minus theta, which then makes this theta. It makes it very complicated. Okay, there's a lot of other angles we have to worry about when trying to find the x component of the force of friction, or the y component of the normal force, or all this kind of stuff. So here's what we do. Okay, let's see if I can sort of erase. Yeah, it's working the way I wanted it to in the first place. Yay! Okay, so what we're going to do is we're actually going to change the way we write our axes. Okay, we're going to change it. So here's what we're going to do. Let's go with blue. Okay, remember, Mother Nature doesn't care how we write our axes, as long as we're consistent throughout the whole problem. All right, so what I'm going to do is I'm going to take my axes and I'm going to rotate it, just like that. So now this, sorry, you kind of see my head all crooked. I'll do it this way. This will be our y-axis, where this is going to be our positive y. And this will be our x-axis. And I'm just going to call this our positive x. Okay. Now, by doing that, it makes things much easier to draw our axes. Okay, it makes it much, much easier. Okay, so let's take a look. If we were to now write our net force equations, right, we're on step 2 now, how would that look? Okay, well, in the x direction, we would have 2 forces. Okay, gravity now has these different components, so we would write the x component of gravity. Okay, and that's kind of pointing downwards and to the right. And then we have friction, which is actually along the x-axis. Okay, and we're going to subtract them because they're in opposite dimensions, and this equals ma. Okay, now let's take a look at our y-axis. Okay, well, we see that normal force is along that positive y-axis, so we say that's normal force. And then we subtract the vertical, sorry, not the vertical, I got to change that. The y component of gravity is pointing in the opposite direction. So FGY equals MA. Okay, awesome. I dig it. Now, the reason we switched that was so we didn't have an MA in both equations. So by saying, like, let's go back to the green because that was our acceleration, right? By saying that this is our x, and if our acceleration is going to be this, that's only in the x, which means there's no, there's none of this going on with the block. So this term is 0, right? That y acceleration is 0. So we can just plug that in right there. Boop. Oops. Boop. Nope. Still an eraser. Boop. There we go. Awesome. All righty. Great. Now it's time to kind of figure out how we can maybe find an acceleration or whatever it is we're looking for. Okay. So I'm actually going to erase the picture because what I'm going to do next is another one of the key changes. Okay, so the first key change was normal force is no longer, vertical, right? It doesn't completely go in the opposite direction of gravity. Second key change was we shifted our axes. The third key change is going to be how we use these changed axes to find the x and y components of our gravity. Okay, so here's what I'm going to do. I'm actually going to even erase this. I'm going to redraw it, but only with gravity, because that's all I'm going to care about at the moment. Okay. Okay, since the friction and the normal force are along those axes, we don't have to worry about anything with components, right? It is what it is. It's the gravity we care about. So do my dot. I like dots. Okay, and here is the gravity vector, right? Okay, and I'm going to make my blue axes here, right? So remember, this is y, and this is x. Okay, now through some geometry, I guess is the best way to put it, we find that this angle right here is actually our theta. So the theta, so if we have our thing here, right, here's theta, those two angles are the same. Okay, I'm gonna erase this again. Oh no, I lost some of my line. This is just careless. Okay, so that's good. All right, I'm gonna change colors again. Let's go with, let's go with, we've done green. Let's go with pink. There we go. I like that. That's nice. Okay, so now what we want to do is we want to identify our components, our x component for gravity and our y component for gravity. Okay, so I'm going to do this. Okay, the x component will be the part of gravity that is parallel to the x-axis. That happens to be here, right? Because we want this to be 90 degrees. So this is, I'm going to do f, g, x. Okay, which then makes this right here our FGY, right? So what does that all mean? Well, remember, we're going to have to use some trig. Okay, so let's look at FGX. I'll go back to my pink. Let's see if I can find it. I don't know if I'll be able to find it again. If not, whatever. Yeah, there it is. Hooray. Okay, so we said FGX, and we're trying to find something for that. But what side of the triangle is FGX with this little kind of gold pink triangle I made? That would be the opposite side, right? So if we did opposite divided by the hypotenuse, which is our gravity vector, that would be equal to the sine of theta. Okay, doing some cross multiplication, we see that the x component of gravity equals the gravity times the sine of theta. Okay, so we're going to need to use that. Now going back to our kind of goldish yellow, okay, we see that FGY is the adjacent side of this triangle. Well, if we do adjacent side divided by the hypotenuse, we get cosine of theta. Again, do some cross multiplication. We see that FGY equals FG cosine theta. Okay. So all of a sudden, our third sort of change has come to fruition here, right? Whereas before, we always said that the x component was cosine and the y component was sine. Not in this case. Okay, and this is normal, right? Depending on how your system is set up, you might need to do stuff like this. But just so you all are aware, for your course, this is going to be the way, this is the only time we're going to have this switch. Okay, so for the course that you're taking, this is the only time we're going to see this switch. Every other time, x will be cosine, y will be sine. Okay, every other time. All right, great. Now that we know this, let's continue through and let's just kind of figure out what we can figure out, okay? So I'm going to do some erasing. Just get rid of all of this. Okay, so and those are really all the only changes that we'll see. Normal force has to be perpendicular to surface, so it's no longer to be vertical. The The axes will need to be rotated unless you want to have really complicated problems. You can still do it, but it's just much more complicated. And now we are going to say that the x component uses sine, whereas the y component uses cosine. All right, so I'm actually going to write those up here just so we know how to use them. Oops, I keep doing this. FG x equals FG sine theta. I almost forgot it. And then FGY equals FG cosine theta. Okay, great. Now, we might need to find acceleration. We might need to find coefficient of friction. So let's use that equation that has those things, and we'll kind of see. I'm not going to solve and say A equals blah, 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 or mu equals blah, blah, blah. I'm just going to kind of show you how to approach that sort of problem. So let's say we're looking for A or mu, right? The only place that equation shows up, or those values show up, would be in this one. So let's write that here. I'm going to do this. Okay. We'll say FGX minus the force of friction equals MA. Okay. Well, we know from up here that FGX is FG cosine theta. So let's write that down. Okay, because we'll need to know that. Or sorry, sine theta. Minus. And we know just from before that the frictional force equals mu times the normal force. Okay, equals MA. All righty. So we don't necessarily have a term for normal force, but check out right here. It's in our y equation, which is why it's always important to write down all of our net force equations, right? And we can just see, all right, we can add FGY to both sides, and we'll have the normal force equals the y component of gravity. Okay, so plug that in. Okay, we'll say FG sine theta, okay, minus mu times FG cosine theta, right? Because that's what FGY equals from here, equals MA. Okay. Remember that Fg, the force of gravity, equals mass times acceleration due to gravity. So we can write this down here. Theta minus mu mg cosine theta equals MA. Great. Now, real quick, I'm going to change colors just because I want to, really. Notice this last term here, there's an m in this term, there's an m in this term, there's an m in this term. Since there's an m in each, boop, boop, we can cancel it out. All right, I'm going to rewrite this up here where it says g sine theta minus mu g sine theta equals a. So look at that. We still ended up with an a equals. Okay. Now, and we could rearrange to find mu, whatever we needed to do. Now, that's good. We're all set here. But it is very important to understand that you might not be able to cancel out the mass every time. Okay. So let me erase, and we'll take a look. Okay. This is nice and big. Yeah, big eraser. Okay. So the example that I just gave, the example that we just worked through, you can cancel the masses, right? Because there was nothing else acting on it. Okay, so let's erase all this stuff. Okay, but if let's say I had a an inclined plane, right, and there's a block. Oh, okay, if say for example there was a person pushing the block up the ramp, or maybe there was a string pulling up the ramp, or maybe that string was attached to another thing. Well, then we have other forces acting on the block, and we can't cancel out the mass. Okay, so just be aware of that. Okay, that's why it's so important to draw your free body diagrams and write your net force equations, making sure to include every single force. Okay, that is the key piece here. You've got to include every single force. Okay, just as a couple quick final bits. These types of questions, we have a pulley on this, aren't super common, but they could occur. One thing I have seen in the past is you still have this, but there's an angle here even. Okay. Now that one becomes a bit more complicated, but this one still follows the x's cosine, the y is sine kind of thing. So you can kind of play with that a little bit. So just make sure you take a look at the problem. Make sure you've got all your forces in the right direction and using the correct trig. I don't expect too much of a question like this, but it can happen. You never know. Okay. All right. I think that pretty much covers everything. I didn't give any numbers because really the key thing is knowing how to be able to set it up. Okay, so being able to set it up, work through it, solve for the variable that you want to solve for, and then plug in numbers at the end. That's really what I'm going for. Okay, so without much further ado, I guess that's all the ado has been done. So we'll call it there. I hope this was helpful for you, and I'll see you next time.